Gelmiş.
Hoş geldiniz hocam.
Hoş bulduk. Merhabalar. Nasılsın?
İyi, teşekkürler geldiniz. Kamera oraya mı alayım? Kamera oraya mı alayım? Benim tamam gereken bir yer var mı?
Sıkıntı yok ya. Yani çok şey yapmıyorum. Zaten diyorum herkesin. Lütfen değil.
Şöyle.
Okay, welcome everyone. Oh, much more than I thought. Today we have a speaker, Tümer. Let me just read it from here. She's an observational astrophysicist. Received her PhD from Beyazit University. Then moved to University of Utah to work as a postdoc. And then, since October 2022, she's been at MIT for her second postdoc actually, working with Marshall Bowles, Michael McDonald, and Eric Miller. Well, she'll, I guess, talk a lot about, but her most of the experience is on X-ray data of clusters of galaxies and so on, I guess. So thank you very much again for this very nice talk, and go ahead, it's yours.
Thank you for the introduction. Thank you for inviting me and coming here in this very hot day. I appreciate it a lot. Today I will talk about galaxy clusters and X-rays, what I do, a little bit of background, and then most importantly I want to talk about the near future of X-ray astronomy, because I see a lot of young people here and they want to know what's going to happen in their future also. I will give a brief overview about my work, and it's going to be about the X-ray universe, galaxy clusters, and the object, and the information that we get from them, and then the instrument of how we measure that information. And then applications are my own work, and then I will talk about the near future XRISM that will be launched in August. So I know I cannot dazzle you by saying that the gold you're wearing is coming from the stars. You all know that, but maybe I can make you think a little bit by saying that we only know the 5% of the universe. And 70% is the dark energy, probably. We don't know that either. 25% is the dark matter. We're trying to figure out how it works. And ordinary matter only composes 5% of the known universe. And in that, we have hot intergalactic gas, galaxy clusters, stars and galaxies, and so on. And most of the time, we don't know how this ordinary matter is interacting, which is challenging. But let's be optimistic and talk about what we know and what we can figure out. The X-ray universe shines bright, from stars to supernova remnants to binary systems and supermassive black holes. But most importantly, we have galaxy clusters, which is the topic of this talk today. Let's talk about how matter is coming into life. Before everything, we had gravitational instability regions in the early universe, and they grew. So these were denser than the cosmic average, and they collapsed under their own gravity, creating these filaments. And at these filament junctions, you're seeing the zoom-in picture of one filament. You have galaxies, and larger connections, you have galaxy clusters. This is a simulation of this dark matter distribution. Illustrious project, they have many nice simulations. So galaxy clusters are basically dark matter halos. They're following the gravitational potential of dark matter, and we said they make most of it. And on the left, you see the dark matter distribution, and on the right, it's switching to the gas distribution, showing that gas is following dark matter. This is the first approximation, and before we knew that these things emitted in X-rays, we just saw them as clusters of galaxies and some space between them. There was also stars, but after we could see things in X-rays, we saw that there was this very bright gas plasma shining in X-rays, and this is called the intracluster medium. Furthermore, when we look at the motion of the galaxies within the galaxy cluster, we actually saw that there is a huge potential there, literally. And this is, the blue is the dark matter that you're seeing. This is a merging galaxy cluster called the bullet. So galaxy clusters are the largest isolated systems in the universe. So it means that you can get almost all of the information about the universe, all interactions, by just studying them. They are the end product of hierarchical structure formation. It takes gigayears. So it means that it is grown by little from stars and the clusters of stars, galaxies, and they grow. So therefore, they should all be self-similar objects. But I said their formation is gigayears. We cannot observe it. But if you look at enough clusters and sample them, you can see their evolution. And basically, this is one of the things that I'm working with. They're important probes of cosmology. When I showed you the dark matter distribution or the intergalactic gas and so on, since these are isolated systems and largest objects in the universe, by just looking at the galaxy clusters, you can constrain a lot of cosmology. The intracluster medium that shines bright in X-rays is a very hot and dilute plasma, like 1 particle in a decimeter cube. Very dilute. That fills in between the galaxy clusters due to many different processes. For instance, when there's a supernova, the galaxy potential is not strong enough to hold all the material, and it just spreads out in between the galaxies. So when we assume hydrostatic equilibrium, there are probes of chemical enrichment histories of elements, cosmological constants, and large-scale structure evolution. This plasma is virialized, meaning that it contains and confines the traces of past events. So what happens in a cluster stays in a cluster, unless they merge. The emission coming from these galaxy clusters are mainly through breaking radiation, which most of you know, bremsstrahlung. When an electron goes into the electric field of an ion, so of course these are all stripped from their electrons, everything is ionized. This is what plasma is, it's very hot. And then the photon, due to the deceleration of the electron, is emitted in X-rays. This is one signature we get from the galaxy cluster plasma, intracluster medium. Another one is the line emission, where an electron, if it's bound to an ion, it's excited and it's de-excited and then emits photon. So this the excitation energy is like a fingerprint of all elements and all electron orbits. So you can see what elements there in the galaxy clusters. And this is how the spectrum looks like. Different colors show different distributions for hotter X-rays. So it means that if the X-ray is hotter, you will not be able to see the bend of the Bremsstrahlung, where we capture the temperature of the gas. So when it gets hotter, you have hotter electrons, so this distribution widens. And those are the line emissions, but this is of course theoretical. We don't have instruments can do those line emissions yet. X-ray spectroscopy is important because while images allow us to count objects, we can explore their morphology. When we measure the photon energy, it reveals the astrophysics behind it. So what is producing the light? How hot is it? Is it an equilibrium or a non-equilibrium or a transient state? Is it moving around? And many other questions can come from the spectra, how the photons are distributed through the energies. So this spectral continuum, the emission features, it has emission features and absorption features, because when we're looking at galaxy clusters, there's a lot of things in between us that causes absorption features. So for these, understanding these, photon energies must be precisely measured. When we identify, trying to understand galaxy clusters, we're trying to go basic and we're trying to put them in boxes, so to speak. So in basic terms, we have co-cores and non-co-core galaxy clusters. So whatever I say for the left is the opposite for the right. So these cool cores somehow are cooler, they're still million kelvins, but cooler than their environment. So the central temperatures are low, as opposed to the bullet cluster I showed, which is a merger. And they have short cooling times, as well as small BCG X-ray peak offset. BCG is the brightest cluster galaxy. It sits at the bottom of the potential well, the center of the galaxy cluster. It grows and grows, so it's called brightest galaxy cluster. And the X-ray, if the plasma is not distributed, is very close to this galaxy. And this is a parameter to look at when we're trying to identify these. This is, of course, not the whole story. So the problem with cool cores, or shining objects in the universe, is if something is shining, it means it's losing energy. And I'm saying these are objects of gigayears or 5 gigayears volt. So it means the plasma is cooling. But when we look at the cooling rates, by looking at how bright the cluster is, we see that cooling rates are shorter than Hubble time, their life. So it means that clusters should not be shining hot in X-rays. So there is a problem there, which was thought that there was molecular gas that was running into the centers of the galaxy clusters. But after we launched Chandra observatory, we could not see those molecular clouds, and it was called a cooling flow problem. What happens to these clusters? So we need to reheat the cluster somehow, and there are possible heating mechanisms. They all work, but sometimes one of them is more dominant. They're called from supernovae to thermal conduction, where the outer radius gas is conducting heat and heating the central region. And we have active galactic nuclei, turbulent heating, when we have galaxy cluster mergers or galaxies falling into those clusters. But so active galactic nuclei is also the supermassive black hole that accrete material onto itself by its pure gravity, and it can reheat the cluster by jets and winds. And this is a simulation, and we are thinking that this central region, this size of the grape, is heating the cluster to hundreds of kiloparsecs. It's a crazy idea, but seems to be working. And the beautiful thing about the AGNs is that, like I said, they can act at very, very large distances. And you can see the intracluster medium. This is Chandra image in X-rays. And you're seeing these AGN jets in the radio emission due to the synchrotron, where you have these electrons gyrating in the magnetic field because AGN is throwing jets. So this is one of the ways how you can reheat the plasma. So we talked about AGN, we talked about cool cores. Let's talk about galaxy cluster mergers, which is basically what I've been doing since I started my postdocs. So they are the most energetic events in the universe, the most. But this is integrated over time, 10 to the 64 after 20 doesn't make sense anymore. And through these mergers, we have shocks driven into the intracluster medium. It heats and compresses the plasma in it, and then in addition to turbulence and bulk motions. So tracers of these events are what we call shock fronts and cold fronts. And radio relics and halos, although I do not work in radio, I really need the radio data to support these traces of galaxy cluster mergers. And then inverse Compton emission, which we will talk about soon, which it is yet to be proved in galaxy clusters and dominance. We characterize shock and cold fronts by the surface brightness and temperature jumps. So we have two plasmas colliding, and they have different properties, density and temperature. When they collide, you have this shock front, and the mediums are very different. This shock front happens very abruptly. Also, radio relics are formed, relics and halos are formed via merger shocks and turbulence. While merger shocks create radio relics, we believe turbulence are creating halos. So let's look at the non-thermal component. I've been talking about the thermal component, which is what we call when you have this pool of electrons. They're all in equilibrium, they're distributed Maxwellian, everything is easy to figure out. But what about the non-thermal things? For instance, what happens when you have a magnetic field and those electrons in equilibrium try to gyrate all of a sudden and things are mixing up? These shock waves reaccelerate these relativistic electrons. We're thinking there's a pool of population of relativistic electrons already within the galaxy cluster, where and these relativistic electrons upscatter cosmic microwave background to X-rays. And we call this inverse Compton. So the photon gains energy, inverse Compton. If it loses, it's Compton emission. And this is why we need the radio. This radio emission, the same relativistic electrons are also gyrating through the magnetic field, and then it gives up in radio emission. So it's influenced the non-thermal pressure on the intracluster medium observables. Most importantly, its mass is still not well established. And when I was talking about how we're sampling the galaxy cluster, we're looking at their temperature and masses and trying to have these scaling relations. So we need to correctly measure the masses. And when we have these mergers, we have thermobrandstrahlung that I was talking about, some line emission, and then inverse Compton that we can connect with the synchrotron. And when we combine the knowledge from them, we can actually constrain the magnetic field, which is the cause of this non-thermal emission, basically. So how do we observe this? We have a fleet of X-ray instruments, and some of them are dead, some of them are really old, and some of them have great potential. And I basically work with Chandra, XMM-Newton and NuSTAR. Hitomi, I will talk about Hitomi at the end of my talk, and it was launched in 2016, but we lost it within a month of launch. It died. So it was very dark for a while, literally in the community, but XRISM is going to pick up the pieces and hopefully do the science that it was going to do. And the X-ray fleet, they all have different properties. It depends on how much spectral resolution you want, how much spatial resolution you want. So depending on these, we build these detectors and the mirrors. So since I've been working with NuSTAR a lot, and most of you know Chandra and XMM, also NuSTAR, but I use NuSTAR in extended source studies. So I will focus on basically how they work. So we have mirrors and detectors. We have mirrors, but how do we capture X-rays? Because when you send an X-ray, it's mostly absorbed, right? It's very high energy, it goes in through the material, and then we cannot focus energy, but we need to focus them so that we can detect them. So focusing X-rays using grazing incidence. Basically, you need to capture the X-rays at a very, very small angle to the mirror so that the distances between the structures of the mirror coatings are actually very small, smaller than the wavelength of X-rays, and then you can actually detect them. NuSTAR uses a crystal detector. There are different detectors around. We have CCDs, charge coupled devices, and we have crystals, and then we have, in the future, we will have microcalorimeters. And of course, there depends on how much, like I said, resolution you need and so on. So these are semiconductors. Basically, within each, we have a lot of pixels, and when you get the photon, the energy is distributed, and that's how you measure. If you have a charge coupled device, it gets the energy, it actually measures the charge that is caused by the photon. It's a different way of detecting the photons, but the reason why NuSTAR has these crystal structures as opposed to CCD, which has better resolution, is that it can capture high energy photons. And NuSTAR was launched to study very high energy events like Aegean, but then we use some background analysis and background tools so that we can study extended sources as well. So when you look at the thermal and the non-thermal contribution, you can see if something is really hot, we need better photon collecting capabilities. And you have Chandra, you have XMM, and you have NuSTAR. So this curve shows that when you have an 8 kV temperature plasma, ICM, if you have inverse Compton in that plasma, and your effective area, your capability of collecting photons drops before 10 kV, let's say, you will not be able to tell the difference between inverse Compton and thermal branch travel. So it's really important to have this information clear. Okay. So this is all the information that we need so I can talk about my work now. I call this the applications. I will talk about 4 different cases. So one of them is a mini cool core. When I was telling you about the cool core cluster and a non-cool core cluster, there is another class of galaxy cluster that are cool core, but in a very small scale. They're called mini cool cores. And we're thinking there can be a transition stage in the evolution of non-cool core clusters into a cool core lag systems. The other 3 are very interesting galaxy cluster mergers. So this is one is a late stage. You can see the relics formed. When you see the relics, it means that this galaxy cluster has been through a very violent merger. The shocks have propagated through the periphery of these clusters, and you cannot even tell the central BCG, brightest cluster galaxy plasma in between. They're all late stage mergers. Then we have this early stage merger. We still have relics, but they're not propagated as far as this one. And we can still see that these subclusters are merging in the merger process. And then we have a very well-known galaxy cluster merger that will be done in some giga-years, which we won't be able to measure or observe. So it's called 3391 and 95, and 91 is also going through a merger within itself. This is one of the first slides of the Eurosita telescope, which is not operating anymore. To start with the mini-coal cluster, it was the work I did for my PhD, and it was very interesting to me how these little structures, like we said, the supermassive black hole, or just a tiny kiloparsec scale galaxy can affect the identity of this cluster of a megaparsec. And what I did in this work is that I looked at it with Chandra and XMM-Newton, and basically, even if you look at it with Chandra with a higher spatial resolution, maybe I'm getting too close to that, no? Tam ekranımı yapayım mı? Okay, I'll stay here. Ben anladım. So we have this, you can even see this in the temperature, in the KT map, temperature map, you can see this cool region. And it's like a couple of arc seconds, it's 5 kiloparsecs, usually cool cores are, can extend up to hundreds of kiloparsecs. And what was interesting about this case was that there was also some tail, which we think is ramp pressure stripped tail of a galaxy, because it somehow went through a merger or going through a region, and when it's going through the environment of the cluster, its material is stripped due to ramp pressure, hence ramp pressure stripping. So what we do in the analysis is that if we have a cool core, we can draw radial profiles because we have a central region and everything looks symmetric, and that's what we did with XMM-Newton in Chandra. And you have that surface brightness, and on the right you have the temperature. Basically, this is how cool cores look like. So you have cooler region and it gets higher. But what we did differently in this work is that we saw that when you deproject the radial profile, meaning that you strip the information from the outer regions of this 3D object that we're actually seeing in 2D, you can construct the central temperatures correctly, and flat means without a gradient means isothermal. Somehow this cool core, this mini cool core, despite this very hot environment, is pushing against the thermal conduction. We don't know how. Probably magnetic field, but this is the answer we give to everything we don't know. Also magnetic preconnection. So we define this interstellar medium, interface, and ICM, intracluster medium. So we're saying that these corona, after this, we looked at different regions and the literature found this gradient, but like I said, when we did the deprojection technique, like peeling an onion and the information, so we can only see the core information, we saw that there is actually an isothermal plasma. And at the end, when we looked at the cooling and how much the AGM power we could find is that the possible heating mechanism is AGM feedback. And this was the first time when we said BCG corona may be isothermal. Of course, we say maybe. You have to be very careful about making very strong claims if you're a PhD student. And what is suppressing the thermal conduction is not yet known. And these may be how cool core clusters are reborn after mergers. And the next one is this beautiful galaxy cluster late stage merger that I was talking about. And you're looking at a radio image. And you're seeing the relics, and relics are formed, like we said, when we have the shock wave and this very high energy electrons are actually accelerating particles that are already in the periphery and creating synchrotron emission. These are called radio halos. These are the contours. And we still don't know what is causing them, but they're called, after the clusters merge, there's still turbulent plasma, and they may be caused sustaining this synchrotron emission. So this was a study done by Chandra, but if you remember, I showed you the effective area, the collecting capability of Chandra and his NuSTAR. And when they were looking at it with Chandra, they saw that there were surface brightness jumps. Chandra is perfect for that because it has very nice spatial resolution. So it can say that there's a lot of photons here and there's a huge drop here. Where NuSTAR, where you can detect very wide band of temperatures, due to this crystalline structure that gives you this beautiful information, it constrains your power to spatially resolve where these things happen. So we use Chandra and NuSTAR injunction. And when I saw this paper and there was a jump and they were saying, we could not measure the temperatures because it's high, and I said, let's observe it with NuSTAR, and I got what I was asking for as priority B, and this is how the beautiful data looked like. So when you look at the image, the first thing we do is look at the image and then decide on interesting features, and then we go select them and do the spectroscopy. And first of all, 3 to 10 kb is a very wide bandpass, even when you're talking about Chandra and XMM. But you can also go higher with NuSTAR, 10 to 20. And this is where I said the inverse Compton, the non-thermal emission, can be separated from the thermal emission. So meaning when you say there's a hard emission, there's either non-thermal emission or a very, very hot gas, or the combination. So this was a very, very long paper, and I'm going to summarize. We first looked at the surface brightness variations. This is what we call a GGM filter, Gaussian gradient magnitude. It basically shows you the gradient, how things like when something is bright, it means that there's a huge change in surface brightness. And we saw those features. Then we made a temperature map, a basic map assuming everything is one temperature model and big pixels. And we also looked at the X-ray and radio clues. When we put them all together, we found this hotspot. We still don't know what that is. It was hotter than the center of the galaxy cluster. We still don't know what that is. And we saw another surface brightness edge candidate. So why is this interesting? Because when I'm talking about shocks and I'm showing you relics, this cluster already has formed shocks, and they're already propagated outwards. So we don't have a lot of shocks observed within the central regions of galaxy clusters that are already merged. So we wanted to see what's going on there. So we decided on regions of interest. Mind you, these are some regions. This 7 to 8, 9 to 10, and 3 to 4 is where we saw some surface brightness jumps. So the basic idea is to see whether there's a temperature jump. If there's a shock front, then the inner region, if the shock is propagating, this inner region means that it's already being heated and it's going towards a cooler structure. So we need to see a temperature drop between these regions. Most of them are smaller than NuSTAR's point spread function, meaning that you really don't know how we get the where we are getting the information, because this PSF is a Gaussian distribution and it has very wide wings. So when you're looking at a center, you're looking at a lot of electrons, a lot of photons coming from that region. And we worked on an analysis tool, and then we figured out how to look at the contamination from other regions. But if you have any questions, I can talk about this later. But in the end, these are the 3 different regions that I was talking about that we saw the surface brightness jumps. And we confirmed they're shock fronts because there was also temperature drops with NuSTAR data. These are very weak shocks, and in the end, when we were talking about this local IC, and I said, we don't know how these radio halos are formed. One idea may be non-thermal, and I looked at different regions within the galaxy cluster and other regions within the radio halo to see if there's something going on non-thermally. So within these 5 regions of interest, looking for the inverse Compton. Even if there's inverse Compton, it should be very subdominant. So when you're looking at very hot regions of the galaxy clusters, it won't be captured. So we looked at this radio profile and we did different models, putting in just single temperature model and then adding thermal models. But the statistics told us that there is a possible evidence of inverse Compton emission within the radio halo, but in the outermost region. And it's also the region where the shock may have reached or not yet. So in the end, when you look at this late merger findings, there is evidence of inverse Compton emission within the radio halo, which may support how these radio halos are formed. And it revealed multiple weak secondary shocks that may contribute to the fitting of these giant radio halos because that's how they may be sustained. But people don't look at it because we can study some things that are really dominant. And you need NuSTAR and Chandra, very detailed analysis. And we're thinking there's a lot more, but we need to see them, we need to study them. And with the method that we did for the large PSF of NuSTAR, it can now constrain the thermodynamical properties at regions smaller than its PSF. The work is like 25 pages, and you can ask me if you have any questions about that. And the second part is, this is a new cluster that I've been working on. Again, I look at the radio, I see the relics, and when you observe something with NuSTAR, you write a grant to, you write a proposal to NASA saying that this is a very important object, and I want to look at it this much, and then they look at it and they give you data and they give you money. So whenever I see relics, my eyes go dollar signs. And when I also looked at the Chandra, I said, okay, we can use Chandra and NuSTAR and study what's going on here. Like the one before, this has double radio relics. Double radio relics are not so rare, but they're rare to see because these clusters have to form in the plane of the sky so that the shock waves can propagate and you can actually observe them, because if they propagate perpendicular to you, you will see a very huge absorption and you won't see any well-defined relics. So there are almost 12 known double radio relics. But the important part is that the other cluster also had this double radio relics, but it was outside of NuSTAR field of view, meaning that I needed to, if I want to study the NuSTAR, study the relics, I would have other problems because the bright center of the galaxy cluster would shine within the NuSTAR field of view, and this is perfect because both of the relics would fit within the NuSTAR field of view. And then we asked again, but when I was doing the feasibility, this was the first time that NuSTAR was going to look at double radio relics within its field of view. And I was honest, and I said, I need this much time to actually calculate how much time I need to study the relics. And they said, good idea, and gave me 30 kiloseconds. And as you can see in the hard band, we have nothing. It's okay, but nothing is also an information, meaning it's probably not hot enough, but still it's a very low data. So I said, okay, I want more because I'm seeing these, I'm seeing this very interesting regions where I can get some, again, jumps of surface brightness and temperature. And when I looked at this temperature profile, this is because when this is from different instruments. You have Chandra, NuSTAR, and NuSTAR and Chandra joint fits. Sorry, I passed it too quickly. As you can see here, Chandra is the blue theta, and then you have NuSTAR. So you're composing one big instrument. Of course, it has some problems. But when I looked at the radial temperature profile, when I wanted to see some drops, some clues of shocks, so that for the first time we can measure shocks actually are within the radio relics. But there is not enough data, as you can see. The temperatures are not constrained, but there may be a shock here. And with this information, I said, can I have some more, sir? And then now NuSTAR will be observing this cluster for a very long time in October. Hopefully we will have nice results. But you do the feasibilities so well that we will either say that there is inverse Compton in the relics, or we're going to say there is no inverse Compton. And the other one is is this PSF study. I can go into that later, but I won't bore you right now. So this early stage merger findings is that we captured a shock front in a relic, may have, and more data is on the way. And this is the last galaxy cluster. Like I said, ABEL 3391 and 95 are going to merge in the future, in the far future. And there's what Iversta says, some filaments in between. So filaments, like I said, are very important at the beginning of my talk because this is how materials are distributed and collapsed and creating these large-scale structures. But these clusters are also touching, so we cannot call these cosmic web filaments. They should be at large distances, but we call them bridges. What interested me with this cluster is that the XMM-Newton showed there was a very hot spot there, around 9 keV, and the cluster is like 4 or 5 keV. And of course, I said, NuSTAR, let's look at it with NuSTAR. This is my first proposal. So I wanted to observe the NuSTAR. I put the NuSTAR field of view, and you're seeing the very bright center, different substructures. They're the clusters that I've already started merging. And I'm putting the NuSTAR field of view somewhere. And what I got was a very high contamination of scattered light, which I was warned about, but I was just starting my postdoc, and I was like, I'll take care of it. And it took me a very, very long time, but I came up with a method that I can actually get rid of this scattered light issue from the data. And it took about 1.5 years, but we have this process, a method, because when I was talking about how NuSTAR was launched for AGN is a point source. But when you're looking at something extended, there's photons coming everywhere. Since NuSTAR was going to look at point sources, they did not put pre-collimators. So, because the photons are coming only from one place. But when you don't have it, the photons are coming in all directions. So basically when you're looking here, you're seeing data coming from here, and it's energy, and also it has also spatial dependence. It's very difficult, but at the end, we looked at the entropy, pressure, temperature, and density of this cluster to see what's going on dynamically. Whether there's a hot spot, is there a shock wave created by the bridge and the cluster periphery? So basically, we could not see any temperature hotspots, nothing at 9 keV, and that's probably XMM-Newton had a lot of noise at the edges of the cluster at the field of view, so it was not constraining the temperature well, as I showed in the previous cluster. But cluster entropy is not the thermodynamical entropy that we know, that we have taught, but it basically tells you what happened in the past of the cluster. So if there's shock waves, if there's turbulence, it increases the entropy. And if you have radiative cooling, it means relaxing and low entropy. And from that, you can see this cluster has gone through a merger or not. So at the end, we could not see hotspot. So the cluster periphery seems to flow into the bridge. So these clusters are basically merging, because if we have some other material than the galaxy clusters, if we can detect the filaments and they're really hot, it means that we can find the missing baryons in the universe. But it looks like this is just a typical merger. What about the future of X-ray astronomy? Chandra and XMM-Newton are old. I cannot say they're working well. They were supposed to work 3 years. Now they're 23 years old. But of course, we have some degeneration. And NuSTAR is in its prime. We're calibrated it well. We're putting some very nice methods so we can study extended structures too with NuSTAR. And StarX is in the future is one of the 2 scopes. It's in the phase A, and one of them would study, one of them would be selected. But these are probes and small scale work. And hopefully we have XRISM that will launch in August if everything goes well. And we have new Athena that was too expensive. Athena concept was, you probably know, too expensive for ESA. So the science and mission design being revisited and will be launched late 2030s. Old, middle-aged, so we need something until the mid-30s. So this is the era of microcalorimeters. When I was talking about the line emission, I was showing you this beautiful graph. It was a theoretical distribution. We cannot resolve that. But with Hitomi, that only operated for a month, we actually saw all of the different lines that was emitted in galaxy clusters. Since it's a microcalorimeter, as opposed to CCDs or this crystal structure, it can actually detect the microkelvin differences. millikelvin differences in the photon energy, it's giving you this beautiful spectrum. Basically, this different iron lines, we see them as just a complex with X-rays. And these line ratios are also important because we also get the temperature information from that. This is how we will know a lot of different things. So it's the X-ray imaging and spectroscopy mission, and it will study the formation and evolution of structure in the universe. These are the four sciences that it aims at. Circulation of baryonic material in the universe, transport and circulation of energy in the universe, and then your astrophysics. So we have two different XRISM instruments. He told me it had better properties, but then of course, since we lost it, this was a recovery mission and we did not have the same budget. And as of last month, I became a part of the team, and I will work with XRISM in the future, and hopefully once it's sent into space. We have resolve and extend. And resolve will look at smaller regions in the sky, but will resolve all of the spectral lines. And extend will have a beautiful large picture of how these big structures are looking like. So I was talking again about the effective area, and you see that XRISM resolve will be multiple times larger than Chandra and XMM, and hopefully New Athena will be similar to Athena, will be a bit lower, but we're looking at a new regime. We will be able to collect a lot of photons and a wider bandpass. And it will, one of the first things that it will do, it's going to observe Virgo, and Virgo supercluster is part of what we're doing, so we're going to look at the nearest cluster, and we have those beautiful jets, as I showed that it was another cluster, and this is the field of view resolve, and with that we can actually be able to resolve those lines, and with that we can see the multi-temperature structure, because we're all thinking that everything is in equilibrium and it's 5 kV, but basically when you're looking at mergers and so on, you have different temperature plasma. And we cannot yet tell them apart, because as I was showing this hot temperature in inverse Compton, and it is even more difficult to tell multi-temperature, because our statistics show that you can fit a galaxy cluster plasma better with just assuming an average temperature. But we want to know whether it is a cooler or hotter component, or it's just all in equilibrium. So the conclusion of my talk is that the universe shines bright in X-rays. The future of X-ray can only shine bright with our contribution. So a lot of new missions, especially New Athena, in this next 6 months is looking for improving the science case for ESA to get the budget that we wanted. So please try to be a part of these things. You can basically just write to Athena and request to be a part of a working group, and you can do collaborations, especially with the new data coming with XRISM, because the future is microcalorimeters. And this can also go through geo observers that you also know with NuSTAR, XMM, and Chandra, but in a year we will have XRISM guest observer opportunities. So XRISM will be showing the full power of microcalorimeters, hopefully convincing ESA to pursue New Athena. And you can put those websites, and looking forward to the collaboration and your questions, and thank you very much for inviting me.
Thank you very much. Any questions or comments or anything?
I have a question. Okay. I'm working on galactic archaeology now for our galaxy merger like Gaia and southern sausage. And before I checked about the article CD galaxies, and I wonder that what is the role of CD galaxies in merger case?
So sometimes it's completely destroyed, and sometimes, like I say, they can retain the information depending on what has happened during the merger. So if it's a head-on collision, we do not expect them to survive. But if there is a collision with some oblique shocks may be formed, and like I showed in the first case, they can somehow retain their information and structures, but mostly they go through REM pressure stripping because they're going very fast in a very different medium. Like you're going through the crowd, imagine you are wearing a lot of things and you have a lot of bags in your hands, and then if you're walking through a crowd that is running at you, you're going to lose some of your bags. And that's why they cannot retain all of their information if it's a very violent merger, but there are some cases that they do. I would not say they have a role in mergers, because merger is not just the central dominant galaxy, but the whole dark matter halo. But it is, of course, the mass dark matter is concentrated because of the inverse square law.
Hi, I have a quick question. Rather, I'm not working in your field, so my questions are going to be perhaps a bit more leveled out. So, so you're detecting a lot of spatial variations, and some of these are relating to shocks, or most of these some internal shocks going on within the cluster. And I noticed you're basically using X-ray emission models to fit these X-ray emission, perhaps shock emission, and etc. Right? In your model. So what I'm trying to understand is what are the nature of these shocks exactly? In the sense, like, are they like completely fully ionized shocks, partially ionized hybrid plasmas, or a combination of things? Are these shocks like plane parallel, oblique shocks? What type of geometries? I mean, are you studying things like those as well? Your sizes are extremely large. I work in galactic, so maybe plane parallel, oblique doesn't mean a lot in your case.
It does.
Won't make a lot of differences. But what I'm wondering is, you're finding temperature profiles and variations. Are you at all testing how well the current plasma models actually as appropriate for the existing plasma? And if they are shocked, or maybe they're not. I'm a bit shocked. I don't know if it's not shocked. Shocked is a bad word. I'm a bit perplexed. Is that because you're going to have shocks of that order in such a large, vast space? You know, how strong are these things? And given that, depending on the strength, of course, there's a lot of matter. But then, are there a lot of matter in the ICM? Because ICM is hot gas and it's very diffuse, isn't it?
It is.
It makes me confused because I'm a galactic astronomer and I know more on supernova remnants and or even smaller entities like planetary nebula, novae, and so forth. So when things are vast and you have very low densities, how well can you actually establish collision ionization? You know, questions like that. You know, these are very vague questions, but I wonder that might be relevant to your research. So I'm wondering how you, because you're showing all these nice plasma codes, but those plasma codes are mostly basic APEC models, or what are you using APEC models basically? Mm-hmm. So APEC models are simple plasma models, but your plasmas look very complex and perhaps involve magnetic field effects. So, I mean, are there any also, I mean, just general comments, and you can make some general comments on
Of course.
Perhaps new models are being like calculated or something, but rather.
So probably when you're working with the shocks, you're using shock models, right? We're using very basic models because we just want to look at the temperature. We cannot go deep as you can go deep because these are very structures that are far away, and let alone just observing the width of the shock. We can only look at the density and temperature, and these are average quantities. So APEC, assuming that everything is in equilibrium, is good enough. Is it good enough? No. We have non-equilibrium models, and there are more different models too, but we don't use shock models because we just want to look at the temperature. And when you say, are you looking for magnetic fields? And this is where we use these inverse Compton models too. So what we're extracting some spectra. We're saying, is this a single temperature model? Is this two temperature model? Is this two temperature plus some non-thermal model? You need very high photon statistics. Basically, with the Chandra curve that I showed you, even the NuSTAR, we'd be lucky if we can get the curve of the temperature right. And when you're looking at somewhere far away, you have this galactic plane, a lot of absorption coming from the galaxy itself, hydrogen carbon density, and it's absorbing your spectra. And it means that you're doing everything you can with very scarce photons that you have. And temperature, like I said, the density are the basic things that we have, but the shape of the shocks, we have oblique shocks, we have bow shocks, and we have parallel shocks that also propagate, but they're moving 3,000 kilometers per second. I didn't write it here because I don't want to believe it. Like 3,000 kilometers per second.
Well, supernova is at 10,000 kilometers per second.
But it's such little.
I know, okay,
regions,
so
right?
the big, I don't know, that would be very, not surprising actually. There is
Everything
if you're
is-
going to have some 10 keV emission somewhere, even 3-4 keV emission, if it's out of shock, that's gotta be over 1,000 kilometers per second. That's basics of shock emission, right? So that's not only normal, we should write in numbers lines.
That's true. But what is different is that when you're looking at supernova and a galaxy cluster, and these shocks are long-lived, it's moving billions of years through the periphery of the galaxy cluster because of the dark matter. So dark matter halos, the gravitation is so strong that we can see in this very dilute plasma. So we have a lot of particles, although they're dilute, like I said, there is a couple of particles here, and sometimes the mean free path is kiloparsecs, hundreds of kiloparsecs. So like an electron can just go 100 kiloparsecs without encountering something else. But since this is happening in a very large scale and a very large potential, then you can keep observing these shocks in a long time. But with microcalorimeters, we can actually see what's going on in there because we still don't know how this plasma is heated. We know we say it's shocked, we say it's diffuse shock acceleration of particles going here and there, and it's accelerating, or first Fermi approximation, but with microcalorimeters and how much line emission we have and the line ratios, we can actually measure the turbulence. And turbulence is what we're basing our hopes on to say that this is how galaxy clusters are heated, but it's in such small scale, and the spectral resolution is needed.
Maybe those calorimeters,
This
those tell
is-
you also about the
Exactly.
plasma as well
Yes.
that you have.
Everything
Not
is
necessarily everything so beautiful, maybe there are combination of things.
their combination. They're most.
So whenever you have some magnetic field impinging on the plasma, you lose the equilibrium effect very easily.
This
So-
is this
So
is
that's
why we
something
add.
you can check with probably better high resolution.
Yes,
That's what-
this is exactly what we want to do.
Disentangle the lines properly.
And we want to constrain this magnetic field because, we're thinking everything is in hydrostatic equilibrium, everything is averaged out, nice distribution. But then when you look at the masses of these galaxy clusters, and we have other probes of looking at masses of galaxy clusters by using Sunyaev-Zaldovich effect, where you have the cosmic microwave background passing through the material, another inverse Compton, but it's regular electrons, not relativistic, so it's only upscattered up to radio waves. And then when we're looking at these cluster masses, we're having a very different, like 10% difference with temperature measured, X-ray measured masses. So there are some things that we're not accounting for, and they have to be non-thermal because we know what non-thermal is. But even we have different models of measuring the temperature, like spectroscopic light, emission weighted, you cannot expect merging clusters to have isothermal. But by looking at the surface brightness in regions, we're doing very basic work here. But hopefully this will be guide to XRISM about where to look. And then we can figure out how the temperatures, how the cluster medium is heated. Does it make sense?
Yeah, I just,
Yeah, it's a very different scale, and time scale is also different.
Okay, so as much as I know, there's tea outside. So any other questions with the tea, I guess. Thanks a lot. Thank you very much.
Tamam, benim bir şeyim yok. Geri çekeyim.